And without further ado, I'm going to introduce our first speaker. We're happy to have her. We have Michelle Woods from the Boeing Company. Michelle has a Bachelor of Science in Chemistry from Pacific Lutheran University in 2007. And after that, she joined the Boeing team in 2008. And during that time, she has worked on all aspects of aircraft interiors, which is perfectly aligned with what we're doing in today's and tomorrow's conferences, which is innovation in interiors, and then UAM and UAV. So in 2018 and 19, she used a self-designed project to mentor University of Washington material science engineering students and the challenges related to bonding thermoplastics. And I know a lot of us on this call are right in the throes of that challenge. And so we're excited to hear what Michelle has to say. And outside of that, Michelle enjoys cooking, sewing, crocheting, and traveling. So without further ado, I'm going to turn my video off and give the floor to Michelle. Michelle, it's all yours.
Thank you, Jason. Let me just get my video started here real quick. And can everybody hear me okay?
You are perfect,
Yes.
Michelle.
Awesome, okay. Just trying to share my screen real quick, sorry. There we go. Okay. Not quite what I was looking for it to do. Scott or Jason, do you guys know how I get?
So we see it, we just don't see it in presentation mode.
Okay.
So view perhaps up top and view in the
There we
presentation.
go.
Perfect, you're good to go.
Great.
Okay, awesome. Cool. Well, Jason, thank you so much for the introduction, and thanks for having me here to talk today. So I'm going to be discussing bonding thermoplastics, Aerospace's unseen challenge. There we go. Okay, so today we're going to be discussing the primary methods for joining or attaching thermoplastics, along with the advantages and disadvantages of each. This will demonstrate why adhesive bonding is the clear choice for expanding the possible usages of thermoplastics in aircraft interiors. After that, we'll review the basics of how adhesives work. Then we'll move on to discuss the two main challenges that are associated with bonding thermoplastics, followed by answering the question, why adhesive bond thermoplastics? We will also review some of the common mating materials, mating surface materials that need to be bonded to illustrate the variety of materials that we work with. To close out the presentation, I'll be discussing what the future might look like to allow us easier and better bonding of thermoplastics. So let's get started. All right, joining thermoplastics. So within the aerospace industry, we have four primary methods for joining or attaching thermoplastics. The first is fasteners. This includes bolts, screws, rivets, press fits, and so on. The second is ultrasonic welding. So for those who may not be familiar with the process, ultrasonic welding involves the use of high frequency energy to heat up and melt plastics. The next is solvent bonding. This process is technically part of a more general category of adhesive bonding and employs a solvent to soften one thermoplastic, and then in conjunction with the application of pressure, results in a bond or bonded joint with another thermoplastic. Then finally, we have adhesive bonding. This method involves the application of pure adhesives, pressure-sensitive adhesives, or solvents to bond thermoplastics to either another thermoplastic or to a non-thermoplastic material. So for the discussion here today, the use of the term adhesive bonding is going to be limited to only cure and pressure-sensitive adhesives. We won't be including solvent bonding in the term adhesive bonding. Now, each of these methods has its own unique set of advantages and disadvantages. So let's review those now. For fasteners, one advantage is the ability to join thermoplastics or thermoplastic parts with little to no training of personnel required. Additionally, verification that materials or parts are joined properly, it's pretty simple and straightforward. It's actually an advantage that none of the other methods have. This method can also be used not just to join thermoplastics together, but to also join thermoplastics materials or parts to non-thermoplastics. The disadvantages, however, of using fasteners includes not having an aesthetically pleasing look to the finished product. This is typically of concern primarily for our customers, as they desire a very clean, smooth aesthetic for their aircraft interiors. Fasteners don't really provide that. From a part robustness standpoint, post-molding or forming hole drilling can result in microcracks or stress concentrations around the hole, and that can be exacerbated by over-torquing of fasteners. Fastener holes that are molded or formed in also tend to be areas of stress concentrations within thermoplastic parts. Now, this is of greater concern when press fits are used as the attachments. And this is due to the fact that press fits tend to require a fair amount of force, and that force can result in microcracks or, in extreme situations, complete destruction of the part. So such an incident actually occurred a couple of years back where we had an injection molded part that used press fit attachment. And this injection molded part was the primary mechanism for closing lavatory doors closed, or latching them in the closed position. The press fits were inserted a little too hard. It caused cracking, and eventually the handle failed in service, and it trapped a passenger in the lavatory for the duration of the flight. Obviously, this is of concern for the entire aerospace industry. So the use of fasteners increases the overall risk of in-service failures, and the risk is increased even further if the thermoplastic part is exposed to things like solvents or harsh chemicals that are used as part of the regular maintenance of the aircraft, or the current disinfection procedures of the aircraft due to the pandemic. Next, we have ultrasonic welding. So it has the advantage of being a very quick bonding process. Usually it takes no more than a few seconds to do. However, the process can only be used on very specific joints, which means we're severely restricted in how this bonding method can be used within our part design. This includes that it's limited to only thermoplastic to thermoplastic materials. Additionally, the type of equipment that would be needed for this method is not something that's readily available in the aerospace manufacturing industry. In order to make this type of equipment available, either the airplane manufacturer or its sub-tier suppliers would have to go out and most likely make a capital investment in order to acquire this equipment. Additionally, once they have the equipment, then they have to train their shop floor personnel in order to carry out the process effectively. So this is a significant impact for what is honestly just a very small number of parts that could be improved. Now, next we have solvent bonding. It has the advantage of requiring very little to no specialized training for the shop floor personnel or specialized equipment like what we just talked about with ultrasonic welding. It can also be used across a slightly wider variety of joining applications than ultrasonic welding. Unfortunately, though, solvent bonding can result in stress cracking or otherwise compromise the overall integrity of the thermoplastic materials as well as the finished parts. The use of solvent bonding may also result in crazing of one or both thermoplastic materials if caution is not exercised during the solvent application process. Crazing can impact both the integrity of the material or part, as well as the aesthetics of the completed part. Additional concerns with the use of solvent bonding to join thermoplastics is that it can only be used to bond thermoplastic to thermoplastic, just like ultrasonic welding. Also, the cure times that are required are quite a bit longer than are necessary for fastening thermoplastic materials or parts or to ultrasonically weld them. So finally, we move on to adhesive bonding. While adhesives, and in particular cure adhesives, do contain solvents, they contain far lower concentrations than would be involved in solvent bonding. Therefore, we have a significantly lower likelihood for stress cracking or other compromising of the part or material. Some amount of caution is still necessary, though, when using cure adhesives in order to avoid the potential crazing of visible or decorative surfaces. Cure times here vary depending on the specific adhesive, but in general, they have much shorter curing times than solvent bonding involves. And when we're working with pressure-sensitive adhesives, our cure time is essentially done away with. So both cure and pressure-sensitive adhesives are already widely available in the aerospace industry, so we don't have the impacts such as needing shop floor personnel to be trained or needing specialized equipment like what we saw with ultrasonic welding. Also, unlike ultrasonic welding, bonding thermoplastics, the use of adhesive bonding for thermoplastics allows us to bond them to either other thermoplastics or to non-thermoplastic materials, much like what we saw with fasteners. So this allows us, in particular, with the use of pressure-sensitive adhesive, to give us that really clean, good aesthetic that I mentioned earlier that our airline customers are always looking for. Now, the primary disadvantage that comes with the use of adhesive bonding, and this is more specific to cure adhesives, is the generation of additional hazardous waste. Uncured adhesives, solvent-wetted cleaning cloths, and other solvent-wetted or solvent-soaked single-use detailing implements are a standard part of any adhesive bonding application. The disadvantage here is primarily due to cost and environmental impact. Now, there is a way to work around this. With the incorporation of appropriate techniques, the creation of hazardous waste can be reduced in order to lower both the environmental impact and the financial impact that is associated with hazardous waste treatment. Now, to recap real quick, the possible methods for joining or attaching thermoplastics, of the four that we've discussed, adhesive bonding is clearly the favorite, at least of this presenter. It can be used to bond thermoplastics to a wide variety of materials. It requires no additional equipment or personnel training that is not already in place in order to incorporate the method. It provides, provided appropriate caution is used when prepping the thermoplastic surface and applying the adhesive, this method is also much less likely to result in the degradation of the thermoplastic part or material. This method also provides that desired aesthetic that our airline customers expect from us. Please do keep in mind, though, that the four methods that I've discussed here are not the only methods for joining or attaching thermoplastics. These are simply the most likely to allow an expanded use of thermoplastics in the aircraft interior across a decently broad range of thermoplastic materials. Of the four methods that we just discussed, two are most regularly used in aerospace, and that is manual fastening and adhesive bonding. So now let's talk about adhesives. So the main question to answer here is, how do adhesives work? Both cure and pressure-sensitive adhesives adhere to surfaces via a process known as wet out or wetting out. Wet out involves the adhesive flowing and filling in the macro and microscopic features of the surface that the adhesive is applied to. Now, this is important because proper and sufficient wet out is critical to get the bond strength that's necessary for a part or material to remain bonded through its intended service life. Now, when we're talking intended service life within passenger aircraft interiors, that can be anywhere from 5 to 10 years, with every 7 to 8 years roughly being the more frequent rate at which airlines refresh their interiors. So now the next question may be, what impacts an adhesive's ability to wet out? Well, there's two primary impacts for wet out. The first is the molecular weight of the adhesive. The lower the molecular weight is, the easier it is for it to wet out against the surface, and therefore you have better bond strength that's possible from the adhesive. Now, the inclusion of additives such as fire retardants or pigments will increase the molecular weight of the adhesive, which then reduces the adhesive's potential maximum bond strength. This is particularly important for use in passenger aircraft interiors, as flammability performance is a critical requirement for adhesives to be able to meet. So we see that we have a challenge here in balancing requirements for the adhesive. The second thing that impacts an adhesive's ability to wet out is the surface energy of the substrate or substrates that the adhesive is applied to. The higher the surface energy of the substrate, the more easily and readily the adhesive will wet out on it. We'll be discussing this topic in depth in the next section. So now let's move on to challenges and benefits that are associated with adhesive bonding thermoplastic parts and materials. As I mentioned in a previous slide, the surface energy of the substrate impacts how well or how poorly the adhesive will wet out. Now, thermoplastics are notoriously low surface energy materials. Surface energies are typically stated in units of dynes per centimeter, but they can be given in dynes per any unit length. The most simplified way to define surface energies is the angle at which something, in this case adhesives, are able to attach and bond to the surface layer of the material which the surface energy represents. So here we have three simplified schematics, and they demonstrate the surface energies and contact angles that are associated with different surface energy materials. The schematic on the far left shows a low surface energy thermoplastic with an adhesive that is attempting to wet out. We can see that the adhesive is only contacting a small amount of the thermoplastic material's surface. So the contact angle is high, and therefore the wet out is going to be minimal, which means a strong adhesive bond to the entire surface of the thermoplastic won't be achievable. The schematic in the middle shows a thermoplastic material of roughly mid-range surface energy. Here we see the adhesive is wetting out a little bit better as it's contacting more of the surface of the thermoplastic and the contact angle is lower. In this schematic, a decent adhesive bond may be achievable. However, it is most likely not going to be sufficiently robust in order to withstand typical in-service abuse that would be expected inside a passenger aircraft interior. The schematic on the far right demonstrates how well an adhesive will wet out on a high surface energy material. We see in that schematic that there is a very low contact angle and that most of the surface of the thermoplastic material has been covered by the adhesive. In this situation, we expect a strong adhesive bond and one that will be robust enough to withstand the possible in-service abuse that we might expect it to have to withstand. So now that we've discussed how thermoplastics, typically low surface energy, impacts an adhesive's ability to wet out and to bond to the thermoplastic, let's move on to the next challenge that's associated with adhesive bonding thermoplastics. That's surface treatments. So surface treatments are used to increase either the surface area that's available for bonding or to increase the surface energy of the material that is being bonded to. That's known as the substrate. First, we have manual surface treatment methods. Those involve abrading or roughing up the material's surface. This is most frequently done with sandpaper, but it can also be achieved with a wide variety of other abrasives. Abrading the surface increases the available area and surface features that the adhesive can bond to. With this, while this method can be an effective means of creating a stronger adhesive bond on low surface energy materials, it does tend to be quite labor intensive. Additionally, if very careful post-abration cleaning of the thermoplastic surface to remove that material that has been abraded off is not carried out, it's very easy to render the treatment no more effective than having done nothing at all. Next, we move on to corona, flame, and plasma treatments. So each of these surface treatment methods works by altering the polymer chains at the material's surface to make them more polar. This increase in polarity at the material surface makes the thermoplastic more receptive to bonding with adhesives. Now that sounds great, right? Well, these methods also have their drawbacks. Corona treatment typically lasts 6 months. Again, that's not bad, but if a thermoplastic part is corona treated and then it's stored for, say, 7 months before it's adhesively bonded to either another part or assembly, then the likelihood of achieving a sufficiently robust adhesive bond may not be good. Plasma treatment, on the other hand, only lasts days to weeks, and the actual duration of how long the treatment is good for is highly dependent on how the thermoplastic material or part is stored. To ensure that plasma treatment lasts as long as possible, the part or material must be stored fully covered and kept clean and dry during the entire storage period. It's a fair amount of extra work. Then finally, we have flame treatment. Now, flame treatment lasts at least a few days, but the actual duration for how long it lasts is dependent on the specific material being treated. This makes the standardization process, if using flame treatment, incredibly difficult. Another hurdle that we have in the incorporation of surface treatment is the cost. Surface treatment equipment can be quite large, thus taking up a large footprint of space within a manufacturing facility. Whether one large machine or many handheld pieces of treatment equipment are purchased, normally a capital expenditure is required for there to be sufficient throughput in order to support production. In addition to the equipment cost, there's also the cost of properly training personnel in order to use the equipment in an effective and safe manner. Both the cost and training time investments have unfortunately made the incorporation of surface treatment generally undesirable within the aerospace manufacturing setting. So a quick recap on the benefits associated with adhesive bonding of thermoplastics. We see that there is a reduction in possible part failures. Great. There's no microcracking or stress concentrations due to hole drilling, molded in holes, or over-torqued fasteners. This also means that we have less susceptibility to chemical or solvent attack from in-service cleaners or disinfectants. And as we all probably know right now, there is a lot of disinfection being carried out on aircraft interiors. So overall, this means that we have thermoplastic parts that have an expected increase in their service life as a result of being adhesive bonded versus any of the other methods that we talked about. We are also able to achieve a more aesthetically pleasing parts, components, and completed aircraft by using adhesives to attach or join thermoplastic parts rather than using fasteners, which is the other more commonly used method of joining. So now that we're all on board with adhesive bonding thermoplastics, let's talk about the variety of materials that would be bonded. So first we have the common thermoplastic to thermoplastic sets of materials that may be bonded. Those can be nylon being bonded to PEC or to other nylons, or something like polycarbonate materials being bonded to polyether amide or polyphenol sulfone. Now, thermoplastic to thermoplastic bonding is a little less common than thermoplastic to non-thermoplastic attachment. Some of the common thermoplastic to non-thermoplastic attachments are nylon or polycarbonate to primed or primed and painted aluminum, or just about any variety of thermoplastic being bonded to decorative laminates. Now, decorative laminates are typically a polyvinyl fluoride or polyvinylidene fluoride based material. So the potential combination of materials here is not unlimited, but there is definitely a very good and wide variety of materials that are represented. As a result, the materials needing to be bonded will run the gamut of surface energies, as I've shown here. Now, accounting for that variation makes standardizing the process while also achieving sufficient bond strengths very difficult, and we need to account for both. What both sets of examples demonstrate here is that the need already exists for very low surface energy thermoplastics to be adhesively bonded. As the use of thermoplastics within the aircraft interior increases, we should expect this need to increase as well. So before we look ahead to the future, let's quickly review the benefits and, most importantly, the challenges of adhesive bonding thermoplastics. As we've seen, the use of cure and pressure sensitive adhesives to bond thermoplastics provides our customers with the desired aesthetic that they expect from us. And it does so across a wide variety of materials and components, as wide a variety as mechanical fastening allows. This in turn presents the opportunity to expand the applications where thermoplastics may be used in the aircraft interior. However, we've also seen the challenges that are associated with achieving sufficiently strong adhesive bonds, given the low surface energies that are associated with thermoplastics. We've additionally seen the challenges present with the current surface treatment options. Those challenges being that the treatments do not remain active for a long enough duration. They are easily degraded by exposure to the environment, to moisture, or just standard handling. And there's no easy means by which to reactivate them. So now let's look at the possible future and what potential it might hold for thermoplastics, surface treatments, and bonding. So knowing that we currently face challenges with the low surface energies of thermoplastics and with surface treatments that are not robust enough for efficient and standardized incorporation into the world of aerospace manufacturing, we can investigate means of addressing both of these issues in a harmonized way. One of those methods might look like adding a more polar functional group to the polymer's formulation, but doing so in a manner that the functional groups are only activated intentionally. That may look like exposure to, say, a very specific wavelength of UV light, or perhaps an application of a mild solvent, such as isopropyl alcohol. Now, there are a few constraints that would need to be associated with such a material development. The first is that these functional groups could not reduce the material's mechanical or flammability performance. The second is that the incorporation of these functional groups could not make the material more susceptible to degradation as a result of exposure to things like UV light, solvents, or disinfectants. The third constraint is that the means of activating the functional groups would not lead to either functional or aesthetic degradation of the completed thermoplastic parts or assemblies. Now, there may be a little bit easier near-term approach. That might be to investigate a more easily and longer-lasting surface treatment. One possible option is a wipe-on surface treatment. This would be something that is akin to adhesion promoters that are already in use with silicone-based adhesives or that have been designed to be used with a specific adhesive. Now, the desire here would be for such a treatment to be effective across most or at least a wide variety of adhesives, as well as being effective on a wide variety of thermoplastic materials. The treatment would need to be preferably non-hazardous, last longer than the current surface treatments that are available, and be easily reactivated, such as with like a wipe of isopropyl alcohol or some other mild solvent. However, the treatment could not result in aesthetic degradation or a decrease of the thermoplastic material's performance characteristics versus what they are without the surface treatment. This would be the key factor in allowing us to incorporate such a method. So with the realization of either of the options that we've just reviewed, or with other new inventive ways to mitigate the challenges of low surface energies and difficult to incorporate surface treatments, we can realize expanded aircraft interior applications for thermoplastic materials. Now, what does this expanded usage look like? In the galleys or lavatories, we could expand the usage of thermoplastic parts for, say, decorative branding of an airline. In seats, again, decorative branding for airlines would be a possibility, or to better serve standard passenger cabin interface needs. Items such as storage spaces in seat backs for cell phones or tablets that are specifically designed for those types of products, for water bottles or other bottled drinks, and for convenient storage of headsets when slipping away to the lavatory, we've all been tangled up in those cords before. It's not fun. Additionally, expanded use of thermoplastics could be realized in business and first-class experiences. Again, more individualized storage compartments for personal items, cell phone charging compartments, and so on. With the challenges we've discussed here being addressed, the sky's the limit for the future application of thermoplastics in aircraft interiors. So in closing, I'd like to thank everyone for attending my presentation. I'd also like to extend my gratitude to SPE for providing me with this wonderful opportunity to share a topic that I'm so passionate about. So without further ado, let's open it up for questions.
So thank you very much, Michelle. And so for everyone that is participating in Swap Card, that was your perfect opportunity to type in those questions. And just so as everyone's doing that, one of the things that I think is good for everyone to feel is that what's the background of most people within SPE? And so you mentioned a couple of things related to polymers and things of that nature. And so that does represent, I think, I don't know the numbers off the top of my head, but I think it's around 18 to 20% of our population are polymer producers. And so hopefully there's some out there that can feed some questions into you. So they are starting to come into my feed. And so Pedro is rapidly typing. Let me try to get one of them for you. So one of the challenge to adhesives bonding is contamination by certain agents such as silicones. Is corona plasma treatment effective in treating a surface that may be contaminated with silicones?
In my experience, it's not. The best way to deal with silicone contamination is to do a full decontamination of this. The use of solvents and cleaning wipes to remove the silicone, whether it be free silicone, silicone oil. That's been the only method that we have found that has been fully successful in dealing with such types of contamination.
Okay, thank you. Another question is, you mentioned the flammability effect of adding functional groups to thermoplastics. What about the adhesive itself? Does it contribute to flammability?
It can, yes. It's dependent on the specific adhesive. Some adhesives that we use do contain fire retardants, some do not. It's also going to be dependent on the size of the part that's used. Some variety of rules. Keith Couliard, who's actually a colleague of mine who will be speaking, I believe it's tomorrow, is probably a better person for the really detailed flammability related aspect. But in general, yes, we do consider adhesives to potentially increase the flammability of these parts and components when we're looking to try to certify the aircraft.
Okay, and you are correct. He is presenting tomorrow, so we're looking forward to that as well. Another question just came in, or what are your thoughts on laser welding compared to the other methods that you had described?
Oh, that's a really good question. So I was recently introduced to laser welding, and I don't have quite enough background on it to be able to speak knowledgeably. I'm interested in learning more about it to see if it's a method that we could potentially incorporate and if it would be any easier in terms of the incorporation into the manufacturing setting itself. Would it be better for training personnel up on? Can we get more use in terms of the variety of thermoplastics? As far as I'm aware, the only big constraint that we would have with that is that it's just a thermoplastic to thermoplastic type of bonding. So it may not be available across all of the material mating surfaces that we'd be looking at.
Okay, and I guess this is it's a play off of that is, how do you feel about chemical bonding? And the example that was given was PBT to PET and PCPPT, or PBT PET to PCPPT. Sorry.
Chemical bonding. So the primary concerns that I have with chemical bonding is that they can, if the application is not very precise and closely monitored, you can have degradation of the thermoplastic. That's something that we have looked into within Boeing. We've found that it's not really desirable because we have had a lot of either issues with there being thermoplastic cracking or crazing that's occurred, and in particular crazing along decorative surfaces where you essentially destroy that, that decorative aesthetic, that appearance item that you're looking for. So in general, we like to stay away from chemical bonding, solvent bonding, anything that's not specifically adhesive where we can really tightly control how it's applied and the concentration of the solvent that's going to be coming in contact with the thermoplastic material.
So I don't know if it's the same answer for this question, but as you were speaking, another question came in regarding chemical bonding. And so that one is related to chemical bonding of materials during the injection molding process, and i.e. a two-shot molding activity.
So in general, we're more comfortable with that because it's a more tightly controlled process. In those cases, there has already been the legwork that's done to ensure that the thermoplastic materials that are being used are going to be able to continue to meet the mechanical requirements that we would have, that there's no degradation of the parts as a result of being injection molded in that particular way. There's just overall a lot more that goes into ensuring that the parts come out the way that we need them to and that they are able to perform the way that we need them to. Essentially, it's just a much tighterly controlled process than if we were to just allow any variety of chemical bonding to be done.
All right, perfect. Someone just asked, have you experimented? Oh, another question came in and it shot it up the screen for me. One moment. Have you experimented with surface oxyfluorination as a means of surface activation?
No, I actually have not heard of that, but I'm interested to know more about that. So if the person who asked that question could get in contact with me, I'd really like to hear more about this.
And so perfect opportunity for that. We have a lot more questions that we're going to make Michelle answer as she's getting grilled for like a 10 in college. But we will have a break after this. And so during that break, I would encourage whoever asked that question. I am not in SwapCard right now. If I am, I get to hear Michelle in two different ears and there's a delay and it creates all kinds of crazy echoes. And so whoever asked that question, please reach out to Michelle and you guys can connect and go into greater detail. Someone had mentioned it's a great highlights of advantages and disadvantages of joining methods. Thank you for that. Are these recommendations general across any thermoplastic and application, or would there be a preferred method chosen for interiors versus, let's say, structural applications?
Yeah, these would be specific to interior applications. For structural applications, there would be very specific requirements that would go along with that. Typically with structures, we have allowables that we need to generate. Most interior adhesives are not capable of having allowables generated off of them. Our structural bonding adhesives are able to go through that process and have allowables generated. So it would be they would be two separate things.
So I had a similar question that I wrote down on my own tied to that. And so it was like, where's the threshold and how do you come about finding it for the interior applications? Does it really, do you anticipate a certain amount of force that it needs to resist? Is there a function that where you, just based on experience, you say it needs to be X amount of strength in order to be here? Or where's the demarcation for that? And how do you come up with it per application?
So do you mean like versus structural applications or just any application within the aircraft interior?
Yeah, so I know that this is, I'm making this up, but if we look into a Stoben and we look at a Stoben bracket, their knowledge not applied with an adhesive. And so obviously there's some type of barrier that once you cross it, you go into a fastener, a traditional fastener. And so how is that evolving over time? And so if we go back in time 50 years where everything might have been a fastener. And then all of a sudden we are getting better and better adhesives, and people are looking at it and saying, well, that really doesn't need to have an adhesive or a fastener with it. So let's go to adhesive. And is that process iterative? Meaning, is it still happening today where we view the next gen, the NMA or any other plane that's out there coming up? Are we looking at revisiting everything based on what the technology is today?
So I would say it is an iterative process. I regularly get questions about being able to move away from fasteners to, in particular, pressure sensitive adhesives, but also sometimes cure adhesives are the appropriate next step, so to speak, to get away from fasteners. When it comes to determining, is this an application that can benefit from adhesives, whether they be cure or pressure sensitive versus a fastener, normally what we're looking at is what does the function of the part involve? What is its application? Is it primary, secondary, or tertiary structure? If that's the case, we're definitely not looking at interior adhesives. Potentially for tertiary structure, we might be looking at structural adhesives. Sometimes secondary structure also, that's a little bit outside of my realm of things, so I'm not sure where their cutoff specifically is. But for interior applications, what we look at is what's the weight of the part? Is it going to be experiencing just shear force? Is it going to be experiencing some other type of force? What kind of abuse is the part potentially going to experience, to ensure that we have a good understanding of how strong that bond needs to be? And then based on that, we're able to determine, does it in fact need to be attached via a fastener so that it is mechanically installed and it's not going anywhere? Or can we transition over to something like an adhesive so that it has a nice, cleaner aesthetic to it? That is something that's occurring more and more frequently. I would say with new airplane programs that could potentially be coming up, I'm anticipating seeing a lot more of those questions come up to get away from mechanical fasteners and probably make as much of a transition to pressure sensitive adhesives as we possibly can, just because the touch time is so much lower. You apply the PSA, you stick it on, you're done. And of course, manufacturing, anytime you can speed up that process, everybody's happy.
Excellent, thank you for that. Just wrote, you mentioned surface treatments that could be easily wiped on and activated. Are there options of integrating surface activation constituents into the thermoplastic instead of or in addition to surface treatment to achieve better adhesion?
Ooh, so I kind of feel like that would actually be sort of a combination of the two things that I was talking about with the functional groups or the wipe-on treatment. I would say that that's, at least based on my background in polymer chemistry, I would say that it is a theoretical possibility that we could add those on. It would most likely look like some kind of addition to the polymer chain itself. Basically what we want is, regardless of how we get there, we want a more polar surface for the adhesive to bond to. So whether it's via surface treatment or functional groups that are added onto the polymer, as long as we have a more polar surface, we will have better adhesion, and that's really what we're looking for.
Excellent. And you had a slide in your presentation that was related to, you said thermoplastics to thermoplastics, thermoplastics to thermosets, thermoplastics to metals, etc. Is there a category within there that is the most common? Or is one like the clear leader, or they're 33% down the road?
It's all over the place. If there is a potential for bonding a thermoplastic to a non-thermoplastic, we're probably attempting it. I would say the ones that I've come in contact with the most are probably the ones that I noted. The decorative laminates, a lot of times we're trying to bond to those when possible. So the decorative laminates are typically on like the sidewalls, that's the what looks like wallpaper, essentially. So we definitely are looking more towards, can we adhesive, whether it be cure or pressure sensitive, onto that type of material. Outside of the immediate aircraft interior, and I mean like what you as a passenger would see, I would say that's where we get into a little bit more of the thermoplastic to primed and painted aluminum. We tend to be using more nylon parts there, and that makes things significantly more difficult because nylon just hates bonding. Super low surface energy. It's a bear to try to bond to something that's super high surface energy like a primed aluminum. That's probably our absolute worst case scenario. And I know that it is something that we have encountered and had to deal with in the past, and had, I'd say, success, but limited success in resolving. So yeah, it really does run the gamut. It's going to vary by airplane model as to what types of material combinations you have. And it's also going to depend on each individual airline customer and what they're looking for within their airplane. Some airline customers will want very specific interiors. Some will go with a more standard package. So that really changes up what the possible options are.
And building off of that, like I flew on a Virgin Atlantic flight not too long ago. And so you see that they have this pink or purple color on the interior. And so when I start thinking of surface energies, the primary question that just pops into my mind is printability. And so do you run into issues? Is there basically a conflict of interest, if you will, or an impasse where optimizing surface adhesion is a negative detriment to printability? And is that something that needs to be concerned going forward?
It can be. I've actually been working on mentoring a colleague who works within the decorative laminate fabrication process. And that is actually one thing that we've discussed, is the printability can frequently interfere with, in particular, the material's ability to pass flammability testing as is needed in like the full certification buildups. So that's definitely, those are competing requirements that we're trying to meet. Can we get good printability and also meet the robustness of the material, because it has to withstand a fair amount of abuse, a fair amount of cleaning, things like that, but keep the printing and that nice decorative aesthetic intact. So yes, that is definitely something that's a concern that I know that we've been looking at as well.
And then this one is for me personally, because I thought I knew something about aerospace, and then I realized I know nothing. It's related to the whole idea of MRO. And so when you're working with something and you have adhesives specified, and if you can't comment on this, then I think everyone on the call understands that. But then what happens, because you mentioned that the refresh of the interior is every couple of years. And so when they're refreshed, is it no holds barred in terms of what's used, or is there still a pretty strict level of referring to specifications that may exist to dive into adhesives?
That's a really good question. And that's actually one that's come up recently with some of our new hires who have asked the same question. So I know the answer to this and I can share it. The way that this works is it's based on the airline. Some airlines have engineering authority that they work with the FAA to get. In those cases, they do have more flexibility in what they can use. They aren't necessarily beholden to exactly what was used in order to generate the type certificate for the airplane. So they may be able to go out and use different adhesives or find different methods of bonding, and they show their own means of compliance to the regulations because they have that allowance with the FAA. For the airline customers that don't have that engineering authority, they are beholden to put the airplane back together essentially the same way that it was built, because they have to show that there is no change to the airworthiness of the aircraft. And if they don't have that engineering allowance, then they aren't able to go to the FAA, show a means of compliance to the regulations, and get the allowance to make that kind of alteration.
Just part of me, I'm taking a note on that. So
No problem.
that was me being selfish and using moderator privilege, I suppose. As we were mentioning that, a comment or a question came in. Can you comment on how cost sensitive these joining processes are for interiors and where the most cost savings slash opportunities might be experienced from the substrate, the adhesive, the labor process time, etc.?
Oh, okay. That's a question. So I would say the biggest cost savings would be whatever allows us the best combination of reduced touch time. So whether it be surface treatments, whether it be thermoplastic materials that come in already with a higher surface energy so that we're able to bond them more easily. And then in terms of the manufacturing impact, what we would be looking at is what requires the least amount of capital investment. So equipment, new materials, what have you. And then the impact for the shop floor personnel. Do they require additional training? Is there safety concerns related to whatever that joining method is? We'd be looking at all of that together from a holistic standpoint to determine what's the overall lowest cost and therefore the most beneficial for us. The time that it takes to get the materials through the process to produce the part or component will also play into that as part of that holistic review. So there's not one specific thing. It's not just a material. It's not just a method. It is the combination of all of them together and determining what is the overall best for the manufacturing environment.
Excellent. That's a great answer for that. I have two more that are on my paper. So this is a last call for those that are out there to get your questions in. I'm using the function that is consumer input. And so how much of this is being driven by the consumers and then how much is, I guess, is it more of a technical push on your behalf, or is it more of a market pull on the consumers, or is it some combination in the middle?
I'd say it's somewhere in the middle. From the aesthetic standpoint, it's definitely more the airline customers. They want the cleanest, smoothest possible look to their aircraft. They want something that essentially someone can just run their hand across and not have to worry about, running it across let's say a screw or a rivet or something that's a sharp metal. So there's that particular part of the input. From the, I would say, aerospace internal industry, whether it be Boeing or other aircraft manufacturers, or even the airline customers as they're doing refreshes on their aircraft, what we want is something that has the least amount of touch time to it. We want to be able to get the process done and over with as quickly as possible. So that part of the input is an ability to increase how quickly we're moving parts through either attaching them to the aircraft interior itself or possibly producing the components that then get installed on the aircraft interior. So it's kind of a combination of both.
So building off of that, I know that on your website, you openly publish how many builds per month that you have for each of the tail numbers. Mm-hmm. If it was smooth as possible and the most beautiful thing ever, it slowed production. Is there a willingness to go in that direction? Or is there some, like for those that are on the line that are saying, hey, I have an idea for this, mm-hmm. and I'm a PSA manufacturer, but it's going to make it instead of, I'm just making up a number, instead of 10 per month, it goes to 9 per month. And obviously when you're thinking about that, the cost is gigantic. And so are there hard, steadfast rules that can't be compromised when thinking about new product development in this realm?
I would say yes, typically. We don't want to see a reduction in the rate. What we would want to see is the incorporation of new methods that would allow for an increase in rate. 737 is actually a great example of that. They are constantly looking at new ways to improve their production process. That's actually where I've gotten most of the questions that I've received related to adhesive bonding, adhesive joining, specifically pressure sensitive adhesives to replace cure adhesives or to replace fasteners. They are always looking for options to increase what they call tack time, their necessary assembly fabrication time within the shop floor. I guess does that answer the question?
No, it does, and
Okay.
and I would imagine as you were speaking, I was thinking about exactly what you just mentioned. Is that most of the time I think we'd be trying to replace something that currently exists, and so it'd be of the mindset, okay, if I'm replacing it, it can replace it to go faster and also be better, and so you're achieving the best of both worlds.
Right, while still meeting all of the certification requirements. I guess that's
Yeah.
the big aspect of that, yeah.
And the last one that I have, prior to letting you off the hook and giving me for our first time seeing each other to be so mean, I guess, is that related to 3D printing. And so 3D printing is this really big hype thing, and people are moving from, I know, from prototyping into industrialization. And so by being creative with how fasteners can be designed through a 3D printing process, is that potentially going in the opposite direction? And I know that you showed your cards and said, hey, I'm this type of adhesive lover, and I have a bumper sticker that proves it. And so can this move the needle in the opposite direction, where we go back to more of a traditional fastener approach using 3D printing? Do you think there's any feasibility in that, or is that a pipe dream?
I personally would be a little concerned with that. I don't think it gets us away from the aesthetics that the customers are looking for. We still need that nice smooth attachment where it just looks like things are all one. For 3D printed fasteners, my concern there would be your options are metal or thermoplastic. Metal, you're not really changing much. For thermoplastic, you would still have the issues with solvent sensitivity or potentially solvent sensitivity, other types of cleaners or disinfectant, attacking those fasteners and them not lasting as long as is necessary. So, personal opinion, adhesive way is probably what's going to get us there. I could be proven wrong though.
Excellent. Well, Michelle, that brings me to the end of all the questions that were fed into the chat and all of the questions that I myself had. So on behalf of SPE and particularly Scott and myself, thank you so much for taking some time out of your day to share with us all Boeing is doing in this area. We have a lot of people that are tuning in right now and kind of seeing where you're headed, and where Boeing heads, a lot of people want to follow. So again, thank you for your participation.
Of course, thank you for having me.
And I would encourage you, again, just a reminder, that person that was talking about oxyfluorination is to reach out to Michelle, because we do have officially a 13-minute break. And so we have some time to refresh your cup of coffee, do some bio breaks if you need to, quick check of the email, knowing that we're all so addicted to our computers. And then we will come back at 1:10 on Eastern Standard Time. So with that, go enjoy Swap Card, go meet some new people. And again, Michelle, thank you so much for your time today.
You're welcome. Thank you.
Take care.
Thanks, you too.